So kind of in a fun way to get started here with section 4.3, let's take a look at the event A. The section 4.3 will be easy. And then we can look at the probability of section A being easy, or section 4.3 being easy. What is A bar going to mean? If A is the event that section 4.3 will be easy, what's A bar?
Won't be easy.
It'll be hard.
And it doesn't necessarily have to be hard, but it just won't be easy. So that's a polite way to say, all right, you're going to have to work a little bit harder on this one. The event that section 4.3 will not be easy. Now, how hard it is obviously going to depend on you, but I would probably say this. Probability that event A happens is 0. It's not going to be easy. What's that mean about the probability of A bar?
1.
Yeah. 1 minus the probability of A, which is 1 minus 0, which is 1. This is not going to be the easiest section of the course. Far from it. Now, is it going to be the hardest? Well, maybe not, but it should probably catch your attention a little bit. Now, part of the reason I did this is to remind you of this rule right here. Does anyone remember what that one's called?
Complementary.
Yeah, the complementation rule. Thank you. Perfect. So let's take a look at calculating certain events. And in particular, let me go back and look at, let's see, our 5% rule here. So let's see here. Here's our 5% rule. It says when sampling without replacement and the sample size is no more than 5% of the size of the population, treat the selections as being independent. All right, that's nice if you can treat them as if they're independent, even though they're actually dependent. So the author's cutting you some slack, saying, all right, let's just kind of take it easy on ourselves here. So let's take a look at the first example from the homework, which is all the way at the top here. In a study of helicopter usage and patient survival, results were obtained from 47,637 patients transported by helicopter and 111,874 patients transported by ground. First part, if one of 159,511 patients in the study is randomly selected, what's the probability that the subject was transported by helicopter? Now this is kind of nice that the problem did for you. Nice little small thing. And that is, you can't say the probability of them being transported by helicopter was 1 out of 47,000. You've got to add up the patients transported by helicopter with the patients transported by ground to get this total right here. That's how many patients are in the study altogether. So if one of those is selected, what's the probability that they were transported by helicopter? I want you to take a second and answer that for yourselves. This is also going to show you, at least in part B, why it's nice when you can apply the 5% rule. It's going to make your life a lot easier. Okay. Let's see. Elijah, what'd you get? What's that probability?
Wouldn't it be 1 out of 159?
But there was a lot of patients that were transported by helicopter, right? Cameron?
Is it 47,637 out of 159,511?
All right, so 47,637 or 159,511. Chloe, do you agree?
Yeah.
All right, yes.
I read it wrong.
Yeah, it's okay. It's all right. I mean, that kind of stuff happens, so no worries. 47,637 divided by 159,511. Now that's for the first patient to be randomly chosen out of this group and transported by helicopter. Can we apply the 5% rule? Can we apply the 5% rule? Well, the answer is yes. Now I think 5% of this is going to be around 7,800 maybe, guessing. Well, what's our sample size?
5.
Yeah, sample size is 5. It's clearly less than 5% of the population. So to calculate this probability, we would do this. We would do 47,637 divided by 159,511 times the same thing, times the same thing, times the same thing. How many times am I going to multiply this by itself?
The fifth.
Yeah, to the 5th power. So since 5 is less than 5% of 159,000, yeah, we can use that rule, the 5% rule. That makes this calculation a lot more user-friendly. Let me show you, and I don't blame you if you don't want to copy down, without the 5% rule. If you do this without the 5% rule, well, then it becomes tedious to say the least. So you're going to get 47,637 on the first one out of 159,511. And then if you're taking one out and you're not using the 5% rule, well, then there's 47,636 out of 159,510. And then we took another one out, right? So now it's 47,635 over 159,509. And then we keep going twice more. 47,634 over 159,508. And finally, 47,633 over 159,507. Somebody quickly put that in lowest terms for me, okay? All right, just kidding. I don't want that in lowest terms. I wouldn't ask it. Can you?
That on the test?
What's that?
Would you want us to write all that out on the test?
Well, the best way to do this one on the test is this way. I mean, this is technically, it's more accurate. This is the exact probability. But my guess is that if you calculate this and you calculate this, they're going to be really, really close. I don't think there's going to be a big difference in there. Yeah, and doing it this way would be a real drag. I mean, you can see it on Nate's face. He's like, oh, are you kidding me? No way. That looks awful. So, yeah, hopefully you'll do it this way. And you can, as long as you do the 5% rule. Now, let me give you a little shortcut on the 5% rule. Let's see, go back here.
How often are we not gonna see the 5% rule?
I mean, it can happen if you're talking about sampling maybe 20 people out of the United States Senate. Well, 20 out of 100 is 20%, so that's more than 5%. So you couldn't use the 5% rule there. But the shortcut for using the 5% rule is, if you want to figure out if your sample size is less than 5% of the population, multiply your sample size by 20. If 20 times your sample size is less than the population, well, then your sample size is less than 5% of the population. So kind of a nice, easy way to look at that. Okay, let's continue. There's a lot in this section. So I want to move on to example B down here. And talks about some probabilities with 3 girls. So let me first give you the sample space for 3 newborns. So we'll start out with girl, 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 and then girl, girl, boy, girl, boy, girl, and girl, boy, boy. Now I've exhausted all the possibilities for these last 2, so now I gotta change the first one. So now it's gonna be boys all the way down for the first one. And then I'm gonna alternate, just like you did for the first 4, I'm gonna alternate those for the second 4. So basically this pattern is gonna repeat itself here. That's how I'm getting these. Now, if you want to know how come there's 8 possibilities here, well, there's 2 genders possible on the first one, 2 on the second one, 2 on the third. 2 to the third power is 8. So that's the size of your sample space. Girl, 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 boy, boy, girl, boy, and boy. So all together, that's our sample space. Yeah, please. Yeah, yeah. Because I mean, well, what's happening is you got the first baby, the second baby, and the third baby. First, second, and third. So that first one can be a boy or a girl. So I've got last one on the first group. Girl, boy, boy. Yeah? They're different events. I mean, these are different things that can happen. Now, I understand what you're saying, and I'm going to get to that in a second. You know, if, as the mom and dad, you're looking at this as the number of girls and just saying, all right, well, I could either get 0, 1, 2, or 3 girls, I wouldn't argue with you. But this is no longer the sample space, because these events are not simple events. Sample space is including all the simple events, and these are different. I mean, if you're going to the hospital and you have girl, boy, girl, or boy, girl, girl, I mean, here, the boy's gonna be the oldest, here the boy's gonna be the middle child. So those are different events. They're different things that can happen, even though the net effect, in terms of the number of girls, yeah, is the same. There's 2. And in fact, if you think about the number of ways that this can happen, you can have 2 girls in 3 ways. 1 here, 1 here, and 1 here. So there's 3 different ways that those 2 girls can happen. So if you wanted to find the probability of exactly 2 girls, it'd be 3 out of 8. Because there's 8 possibilities that are all equally likely, and only 3 of them represent having exactly 2 girls. No, it doesn't, because it's asking you for the probability that at least 1 is a girl. So that can happen in any order and in a number of ways, right? So let's take a look at that probability of at least 1. At least 1 girl. Okay. Well, at least one girl. Let's do it directly, just by looking at the sample space and try and figure out, well, how many ways are there that we can get at least one girl? Well, that's at least one. 1, 2, 3, 4, 5, 6, 7. How come I can't count this one? No girls. Good. So if you're keeping track, there was 7 ways I could get at least one girl out of 8 there. So that's a direct calculation. And I'm hoping that that one's not that hard. So are we okay with that one? Actually, let me suggest you a different way, Skylar. And the reason I'm doing this one slowly and carefully is because I want to show you the second way. And the second way is something you're going to use when you see words like this. At least one, or at most one, or at least 2, or at most 2. That's a big red flag for you when you're doing these kinds of problems. You remember how we started out this section? I started out kind of teasing you, but I also started out with the complementation rule, right? We're going to use the complementation rule. And what I want to show you here is this. Let's call this event A. A is the event of at least one girl. Somebody's hungry or thirsty. All right, that's the event A. What's A bar?
Having at least one.
Not having at least one girl. What does that mean relative to the problem? All boys. So the number of girls would be 0, right? So let's put that, that's A bar, all boys. So I could calculate this probability of A directly, or I could calculate it as 1 minus the probability of A bar. And a lot of times, this is going to be a lot easier than calculating this directly. Your sample space is rarely going to be so small that you can just write it all out. So, probability 1 minus probability of A bar. Michal, what's the probability of all boys?
1 out of 8.
Yeah, 1 out of 8. And so 1 minus 1 out of 8 gives me 7 over 8. And that's it. Now, was this a lot easier, Skylar? No, not really. Maybe a little bit. I don't know. But this is not really the purpose of me doing it here. It's foreshadowing. I'm foreshadowing what's going to happen with some of the other problems that we're going to work in this section. So, we're headed that way. Are you okay with this one as is? So we did it 2 ways. All right, I got a couple thumbs up on Zoom. Cameron?
The 2 to the 3rd power, where do you get that again? How do you know it's the?
Sure.
power? Just real
First, second, third.
quick. Oh, okay.
So that's your first child. There's 2 possibilities, right?
Oh, yeah.
Boy or girl.
Okay, perfect.
And then the second child, and then the third child. And when you multiply all those together, there's 2 to the 3rd or 8 possibilities. So that gave us a mercifully small sample space in comparison to, say, our next problem. So let's take a look at the next problem, unless there's some more questions on this one. In China, where many couples are allowed to have only one child, the probability of a baby being born a boy was 0.545. Amongst 6 randomly selected births in China, what's the probability that at least one of them is a girl? Let me pause for a second. Is there something in here that I warned you about that should catch your attention?
At least one.
At least one. All right, that's screaming out, you're probably gonna wanna use the complementation rule. So, okay, let's follow up with that. Now, if you've got 6 couples, let's see if we can't figure out what the size of the sample space would be if we wanted to list it out. I don't want to. 1, 2, 3, 4, 5, 6. How many possibilities are there for the gender of your first baby?
2.
2. And then 2 again. And this is kind of getting repetitive, so we'll get fancy and write it as 2 to the 6th. That'd be 64. It kind of would be a pain to list out all those possibilities. So let's not. Let's instead look at the possibilities the way I did here, the number of girls. Now you can't say, oh, there's a 1 in 4 chance of having 0 girls because there's 4 events here. That's no longer true because these events are no longer equally likely. So let's take a look at our possibilities in here. Probably need a little bit longer. So this is going to be the number of, let's see, we wanted girls or boys? Which one was it? Boys? Let's see. Oh, at least 1 girl. All right, so the number of girls. So the number of girls. What are the possibilities for, amongst these 6 babies, what are the possibilities for number of girls? What should I start with? 0. Excellent. Or 1, or 2, or 3, or 4, or 5, or 6. So, all right, I guess I didn't need it quite that long. So, hasta la vista. There. We want to calculate the probability of at least 1 girl, so let's let A be the event of at least 1 girl. What I want you to do on your paper is circle all the numbers that go with event A. Circle all the numbers that go along with event A. So what numbers did you circle? What should I circle?
1 to 6.
1 through 6. So that's event A. To calculate this probability directly, not only would you have to know something about the sample space, you'd probably benefit from knowing something called the binomial distribution, which is in chapter 5. But all that's a lot of work compared to what you could get away with doing. What is the event A bar?
0. All boys.
All boys.
A bar, event of all boys. So that's this right here. That's your A bar. So instead of calculating the probability of A, we're going to do 1 minus the probability of A bar. The probability of A bar is going to be a lot easier. Now they told us that the probability of a boy was 0.545. That's going to become a problem in China if you have 9% more boys born than girls. In fact, China, I think, is experiencing a population decline for the first time in decades. And India is going to be passing them up as the world's most populous nation. So, wow. If this is the probability of a boy, what's the probability of a girl?
1 minus that to the 6th.
Yeah, 1 minus that. So it's going to be 0.455. 5. So like I said, there's a 9% gap. That's gonna become a problem after a while. Guys are gonna be fighting each other. I saw her first. Okay. We wanna calculate the probability of all boys. Probability of A bar. There's a probability of boy on the first one, and the boy on the second one, and so on. All the way down to a boy on the 6th one.
How did you get the probability of girls?
Oh, it's 1 minus the probability of a boy.
Oh, okay.
Yeah. I mean, they gave you this is the problem, and then this is just the complement. So that's just for one baby, right? We're gonna have to use that in calculating the probability of all these probabilities. Now, there's something here that's gonna make this nice. If you're drawing these babies out at random, and you look at the probability of having a boy here, that's not gonna change the probability that the next one's a boy, or the next one, or the next one, or any of these. And so, by independence, these events are all independent, you can calculate that as a probability of a boy on the first one, times a boy on the second one, all the way down to a boy on the 6th one. And there's good news here. May feel like, really, what could be good news after all this? But there is good news here. We know these probabilities. What's the probability of a boy?
0.545.
0.545 times 0.545 times 0.545. We get this by independence. It's not going to be something I'm going to hammer you with too much yet, but independence. These events are independent. What's a better way I can write this?
Raise it to the 6th.
Yeah, thank you. Raised to the 6th power. So 0.545 raised to the 6th. Now that's almost what I wanted.
So minus that.
Yes. To get the probability of A, I want 1 minus that. So probability of A is going to be 1 minus 0.545 raised to the 6th power. And it should be pretty high. There should be a really good chance if you had 6 babies that at least one of them would be a girl. So 1 minus 0.545 raised to the 6th. I'm getting about 97.38%. 0.97379, dot, 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 dot. Have you seen this little squiggly sign like this? What does that mean?
Approximate.
Approximately. 9738. So here, you would absolutely want to do the complementation rule. Calculate it directly would be 10 times the work. Comments or questions on that one? I want to do one more like that, and then mention a little bit about independence, independent events. I think there was one more like this in that same series. The SAT, excellent. If you make random guesses for 10 multiple choice SAT questions, each with 5 possible answers, what's the probability of getting at least one correct? If these questions are part of a practice test and your instructor says you must get at least one correct answer before continuing, is there a good chance you will continue? All right, so problem 10. Can anyone figure out how big the sample space would be if we wanted to calculate it? I mean, on the first, you can get it right or wrong. Second one, right or wrong. Third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. So there's 2 possibilities here. 2 times 2 times 2 times 2.
It's 5, right?
Well, I'm looking at, you either got it correct or incorrect.
So it doesn't.
I'm not talking about the probability of getting him correct or incorrect. You're right, it's 5 possible answers, and your chance of getting one correct would then be what? There's one possible correct answer out of 5 choices.
20%.
Yeah, 20%, you got a 1 in 5 chance. So that's 1,024, that would be the size of your sample space. And what I'm politely trying to do is tell you, you're not gonna do it this way. You're just not gonna write out the sample space and go, oh, okay, I'll do it by counting and whatnot. So let's go back to something that I've been trying to condition you about. What part of this problem should jump out at you?
At least.
At least, nice, well done. Is there at least, probability there's at least one correct answer? That's telling you that you're gonna need the complementation rule. We can kind of draw the same thing we did the other day, or the other problem, I should say. This is our number of correct guesses. Number correct. Could be 0, could be 1, could be 2, could be 3, could be 4, all the way up to 10. It'd be extremely unlikely that you would get 10 correct by guessing. In fact, you'd have exactly a 1 in 1,024 chance of getting all 10 correct. So we want the probability of getting at least 10 correct. Let me write out again some notation. A is the event of at least one correct. That's going to be all of these. That's event A. But I left one off. What's this here? A bar. Nice. So that's A bar. So probability of A equals 1 minus the probability of A bar. So let's work on the probability of A bar. That means you get them all wrong. You're a bad guesser if you're getting them all wrong. So what's that mean? Probably the first one is wrong on the first one and wrong on the second one. Wrong on number 10. Just get them wrong, 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 wrong. There's an assumption here that we're going to use to finish this calculation. And it's a reasonable assumption. If you guessed the first one wrong, does that affect the probability of you guessing the second one wrong? No. So they're independent. So by independence, then here's what's going to happen. This is going to be the probability that you get the first one wrong times the probability you get the second one wrong, all the way down to the probability you get the 10th one wrong. Let's take a moment and reflect back. What's the probability of guessing one right on this test? 1 out of 5, right? There's 5 questions, 1 right answer, or 5 choices, 1 right answer. So the probability of getting 1 right is 1 out of 5. So what's that mean the probability of getting 1 wrong is?
4 out of 4.
4 out of 5. And that's what I want to use down here. I've got probability of getting the first one wrong. Well, all right, I got a 4 in 5 chance of that happening. And the probability of getting the second one wrong, again, 4 in 5. Johnny, can you help out my poor hand? What's a more convenient way to write this?
It would just be to the power, like how many are there? 7 or 10?
It'd be to the 10th power. Nice. That's almost the right answer, but it's not quite. What's the last thing I gotta do to get the right answer? Yeah, I gotta do 1 minus that. To get the probability of A, I'm gonna subtract the complement. I figured out the complement. So probability of A equals 1 minus 4/5 to the 10th. And it should be about 90%, I'm guessing, a little bit less than 90%. So let's see, 1 minus 4 divided by 5 raised to the 10th power, 89.26. 89.26. 0.8926. Nice.
But could we leave it as 1/5 to the 10th?
It's the 1/5 to the 10th would be something different.
Oh.
That wouldn't be the same thing as this. 1/5 to the 10th would be really, really, really small. Yeah. All right. I'm gonna make one last comment on probabilities here. It's not test material, but I do want you to understand what's going on here. That's some notation here. Let's see. B. All right. Yeah, it's looking a little bit better here, I think. Let's look at this as opposed to our handout. I'm gonna let H1 be the event of getting ahead on the first flip out of 2. We're gonna flip a coin twice. This is the sample space here, right here. So you could have head on the first one, head on the second one, head and a tail, tail and a head, tail and tail. So there's a total of 4 things that can happen. So H1 is the event of a head on the first flip. And H2 is likewise, except the head on the second flip. What's the probability of H2? Well, it means a head on the second flip. So let's take a look at what that would be. And let's see, draw. So a probability of head on the second flip. How many things are there that can happen altogether? There's 1, 2, 3, 4. Remember, each event is flipping a coin twice and looking at the results. So these are 4 things that can happen. How many of them result in a head on the second flip? 2 out of 4. So 2 out of 4, or that's such a small number where I'd be happy to see that as 1/2. Now, what would change in the probability if I said, psst, I'm gonna tell you a secret. I got a head on the first flip. How would that change things? Well, if I told you I get a head on the first flip, you've got now what's called a new sample space. Instead of having all 4 of these possibilities, you've only got these 2. That's your new sample space. And of those 2, what's the probability that you get a head on the second flip?
Still listed.
Still 1 out of 2. So it's 1 out of 2. Now that thing that I just did for you, I said, psst, hey, you got a head on the first flip? That's called, you would read this as the probability of a head on the second flip given the event that the first flip was a head. So you're telling somebody some information. But the big thing to notice is that these two things are the same. Right? So did knowing that you got a head on the first flip affect the probability of a head on the second flip? No, it didn't. And that's why these events are independent. The outcome of one has no effect on the probability of the other one. The weather in Australia has no effect on your probability of getting an A on this test. All right? Those are just independent events. So we're going to work more with independence moving forward. But for right now, you can use kind of this rough guide that if two events are independent, the outcome of one does not affect the probability of the occurrence of the other one. That's what it means for two events to be independent. All right, that's it for right now for section 4.3. Let me give this one. Any last comments or thoughts here on this? Okay, let me stop this here and wish you good luck.